All right, let's talk about energy. So what we have here is we have a roller coaster. I'm going to call it a roller coaster, but really it's just a box. Um, and it's traveling across this whole mechanism here and then hitting a spring at the end. That's my depiction of a spring. So when we're dealing with energy, we have five main constants or five main concepts to deal with, plus power, which I'll talk about after. Um, we have work done, which I talked about in my system video. It's basically whenever we apply a force over a distance when it was not previously part of the system, hence force times distance. We have a kinetic energy, kinetic rotational energy, a gravitational potential energy, and a elastic potential energy, the S standing for spring. Um, so kinetic energy happens anytime we have motion. If we have translational motion, so basically, if we have a box that moves left, right, up, or down, um, we're going to have kinetic energy, and that is dependent on the box's mass and velocity squared. And because it's velocity squared, we don't care which direction, because a negative velocity will then just become positive. Um, so that means that if this box here were traveling up that way at a velocity v, then that would mean its kinetic energy would be equal to 1/2 mv squared no matter what. No matter if this v was going that way, or this way, it would always be that. But kinetic energy is only dependent on if the thing is moving linearly. K rotational is dependent on if you have, let's just say, a disk or a circle that is rotating about this center point here, center point P here. Um, if it's rotating about this center point P, um, then without moving this way or translationally moving, um, then it would have only K-rotational. And K-rotational is based on the moments of inertia and velocity square or angular velocity squared, which is really just fancier. Um, like if you were to narrow that all down, it's just kind of um, a fancier kinetic energy. Then gravitational potential energy is present anytime you have a height above an equilibrium being zero. So for instance, at this top of the hill here, we're going to have gravitational potential energy because it's a certain height above our 0 point, which we're going to say is at the bottom. And then our elastic potential energy is anytime we have a spring that's being compressed. Dependence on the amount it's being compressed by squared, and some constant related to how compressible the spring is. Of course, there's some springs that are very compressible. They're very easy to compress, which means that their K is a lot lower. And then there are some that are extremely difficult to press, like industrial coils that have extremely high constants, extremely high spring constants. So let's use all of that we know plus power to solve these three problems. The first one says if it takes 10 seconds to get the box up the initial hill with an ending velocity of 2 meters per second, what was the rate energy was added? So this involves the one thing on this list I didn't talk about so far, power. So anytime you see the rate of energy added, consumed, normally those are your keywords that you're trying to think about power. Power is the change in energy divided by the change in time. So if that's what our power is, we have to think about how this is working. Now, of course, we assume that this box is at rest at the beginning. So we're going to have some change in energy that leads to it being at the top of this ledge, and moving at 2 meters per second. So if we have a change in energy, it starts at zero. Zero plus change in energy is going to be equal to our final gravitational potential energy because we have a height involved, and our kinetic energy because we have our motion. It says 2 meters per second ending. Now, how did I get this? I used this equation here, which is your one for all equation for energy. The sum of initial energies plus our work done by the system, change in energy, is equal to our final energy. So I was able to deduce that our initial energy is 0 because there's no motion here. It's not at a height. There's no spring compressing it, and it's not rotating. So therefore, all sum of energies are equal to 0. Then we have some change in energy that results in it being lifted up that entire thing is equal to the gravitational potential energy and the kinetic energy, because we have a height, we have motion there, we have no rotation because it's a box and it says there's no rotation, and there's no spring involved, so there is no spring potential energy. So that means we have, using this equation, this system here. Change in energy is equal to work. So if you'll notice, power is really the change in energy over time, not sum of energy over time. The change in energy over time, which is, in other words, work over time. So the work done is equal to this plus this. So we have mgh plus 1/2 mv squared. Now that we know this, we can solve for this w. W is equal to 4 times 10 times 2 plus 1/2 times 4 times 2 squared. Work is equal to 80 plus 2 times 4, which is 8, so 88 joules, because that is our unit for energy, joules. And then now we have to think about power. It says it takes 10 seconds to get the box up the hill, which means that we can divide work over time to get power. Power is equal to 88 over 10. So power is equal to 8.8 watts, or in other words, joules per second. So our initial power is 8.8 watts. And then now that we know that, we can also put up here, we have 88 joules up at this top thing here. So power is equal to 8.8 watts. I can move all this now. Now that we have that, I can erase this, and then we can go on. So now it says, what's the velocity after the friction zone? Okay, so one very nice thing about energy that we would have to do with forces that we don't have to do with energy is that energy does not, it doesn't matter what happens between 2 points in a system. It doesn't matter if it goes up or down ramps. Energy will always stay constant because it's all scalar quantities. They're all things that describe without direction. So we can model with this same equation again. Initial sum of energies plus work is equal to final sum of energies. So let's just model it with that sum of energies equation again. I'm going to use a different color because I used blue last time and I shouldn't do that. Sum of energy initial plus work is equal to the sum of energy final. So this is our initial equation. Let's think about what are our sum of energies at the initial. Oh wait, we already did that in the other problem, so we don't have to do that. 88 plus work is equal to final energy. Well, after the friction zone, assuming that it's still up there at 1 meter above it, after the friction zone, we have some kinetic energy. I didn't mean to put 1/2 there. We have some kinetic energy plus some gravitational energy because it's still at a height above 0. So now we know that we have to deal with this work here. Sometimes there is and sometimes there isn't a work done on the system. The only time we would have a work done on the system is if there's a non-conservative force or a conservative force that adds more friction, that adds more force, like we saw with the power one, bringing it up to there. So this work here is actually there because we have friction. So we're going to be subtracting the work from it. So we're going to have work due to friction here. So now we have to think for a second, would this work done by friction detract from the energy of the system or add to the energy of the system? Well, if it doesn't really explicitly say that you're adding it, most of the time you're subtracting it. I mean, it just makes sense. Friction slows things down. So you're going to have a decrease in energy is equal to this whole thing. So work done by friction is equal to force times distance. So we know 88 minus work done by friction. Now, force of friction over distance, the distance being 1 meter, so we can pretty much just take that out because anything multiplied by 1 is the same thing it is. So force of friction then is mu times the normal force. The normal force in this instance, because we're on a flat surface, is equal to the weight of the object, the force due to gravity, which is equal to mg, is equal to 1/2 mv squared plus mg. I'm going to say just mg because the height is 1 meter and we can exclude it if it's 1 meter. I'm going to take a sip of water because my throat is starting to feel funny. I grabbed the wrong pen. So now that we have this whole equation here, we can then plug in all of our known values for all these things. 88 minus mu, which it said mu here was 0.1. 0.1 times the mass 4 times the gravity 10 is equal to 1/2 4. We're looking for the velocity plus 4 times 10. Okay, now we can simplify all of this down. 88 minus this number minus that number. 88 minus 4, because 0.1 times 10 is 1, minus 40 is 44. So we are left with 44 is equal to 2v squared. So 22v squared, which means v is equal to rad 22 meters per second squared after the friction. So v after the friction is equal to rad 22 meters per second squared. Okay. Now, I'm going to talk just for 1 second before we move on to number 3 about why I can even set up this equation. So this equation can be set up because of internally how energy works. Energy in a system can switch between any one of these 4 quantities here. It can switch between any one of those. If they're all conservative forces, and these are all conservative energies here. Of course, friction was non-conservative, so we actually saw this 5th one work being done. Excuse me. But of course, if there wasn't a friction there and we wanted to know the velocity from here to this ledge, we could have just done this same equation, but without this here. Because energy in a system where there are no non-conservative forces or non-conservative works acting stays constant the entire time. Meaning that this work here is, it can be taken out because it says, because it would say friction isn't dealing with the whole system. So that would mean that we are dealing with just an initial energy and a final energy, which we're about to see right now. So we now have spring constant if compressed 0.25 meters before stopping. So now we get to use that equation again, except because there's no non-conservative forces or work acting, we can negate the work here. So we say sum of energy initial is equal to sum of energy final. So now that we have this, I'm using red. I don't know why, but I'm using red. So now we have our sum of energy initial. We know because we're up on a height, we have a UG, and I'm going to put initial. Because we are, actually, I am going to put initial. Because we have a velocity at this point, we literally just solved for it. We have a kinetic energy at this point. And we have nothing else. There's no rotation and there's no spring yet. So at this point, that's all we have is equal to the sum of energies there. Well, it says spring constant if compressed 0.25 meters before stopping. So that means it's going to stop at 2.5 or 0.25 meters, meaning it's not moving. Therefore, there's no kinetic. It's not rotating, no rotational kinetic. There's no gravitational because at this spring, it's at 0 meters above the ground. And of course, because we're compressing a spring, we now have we now have elastic potential energy. So then we can simplify this all down and solve for it. So mgh plus 1/2 mv squared at that point is equal to 1/2 kx squared. Now we can plug all the values we know in. 4 times 10 times 1 plus 1/2 4 rad 22 squared is equal to 1/2. We're looking for the k times 0.25 squared. There we go. And now we can plug all of that into our calculator. We say 4 times 10 times 1 plus 1/2 times 4 times 22 times all of that times 2, and then all of that divided by 0.25 squared is equal to 2688. So that means our K is equal to 2688 newtons per meter. So in other words, it kind of just means that it applies 2,688 newtons of force per meter that this spring compresses. Is kind of what that constant is telling you. So now, with all of that being said, we have solved all three problems here. 2688 Newton meters. There we go. Now I'm going to talk one more thing about this system in particular. When you're doing this, it could also be a good strategy for you to immediately label all the points of interest on this system. So one point of interest, because number 1 starts at here, would be at your start. Another point of interest is telling you that you're ending at the initial hill, so this might be another point of interest. Another point of interest is the velocity after the friction zone, which would be here. Now, one thing that you might do is put your next point of interest right before the friction zone, but who cares? Because the amount of energy from here to here is the same. It says that if there's no non-conservative forces acting between 2 and then this theoretical 3 here, that energy would stay the same. So we could just set it equal to this 2 instead of solving for a 3 and then solving for a 4. So this is right after the non-conservative force acts, and then we're going to have another one that says we're going to have a 4 once completely compressed. So those would be the major points of interest. And then instead of saying energy naught equals energy final, we could say the energy at point 1 or the energy at point 2 or the energy at point 3 or 4 is equal to the energies at 1, 2, 3, or 4, given that there's work being done. So setting these numbers here can help you also keep track of where and what things are. Oftentimes you'll see this instead being labeled as height 1 and this as height 2 or something like that. And then that kind of allows you to rule off your points immediately. And that's just a helpful strategy to help you organize your work, and so that you don't plug in a 2 for this one here. Yeah, and then like you can do another thing with this spring here, because springs sometimes have two-parters. You can say one thing it might ask you if you're dealing with a spring is what's the velocity right before hitting the spring. So then you can instead put your 4 here and then your 5 here to solve for the velocity before the spring from 3 to 4, and then solve for that there. If it asks for the velocity right before the friction zone, you could then set your 3 here and then set your 4 here. And then if it gives you the whole thing starting from up here, you can start it at 1, then 2, then 3, then 4, then 5, or something like that. You could just set it to the numbers that make sense to you. All right, now let's talk a little bit about rotational kinetic energy, because that's the only one we didn't cover. Now I'm going to make up a problem here. We have a ramp. We have a cylinder on that ramp rotating about that center point there, where its radius is equal to 2 meters. Let's just say 2 meters. It's a massive barrel. Radius is equal to 2 meters. Mass is equal to 100 kilograms. Mass is equal to 100 kilograms. And this entire thing is at an angle of, 30 degrees. Because that's nice, easy numbers for us. So if this entire thing is at an angle of 30 degrees, then we can talk about, we can try to talk about all this stuff here. Now, when we're talking about a cylinder rolling down a hill like this, actually one more thing I'm going to mention really quick is moment of inertia of this is 1/2 mr squared, which I actually remembered for the sake of this problem, so I wouldn't have to look it up in the middle of this problem. But on the AP test, they will give this to you, unless it's a point mass, where moment of inertia of a point mass is mr squared, and that's something you have to remember. Point mass being like, oh, center is here, and then there's a string with negligible mass that connects to a mass here. That would be a point mass because there's nothing connecting it here. Or like, I don't know. So pretty much that. But one little cheat code too is that if they don't give you the moment of inertia for something that isn't a point mass, likely there's some discrepancy with the problem where it's like, where you'll see like, oh, you can like, you'll see 3 answers and then a 4th answer that says this needs to be, or this can't be solved until we get the moment of inertia. Hey, it has to give you it if it's not a point mass. So likely that's your answer if it doesn't give you it. But don't use that as a cheat code unless you know what you're doing. So, or at least try to solve for it first, and then you can try. So let's try to solve for the velocity of this thing at the bottom. If this height here is 5 meters, let's just say it's 5 meters. So now we can go ahead and try to solve for, and let's just say this barrel starts at the top as well. So, and it starts at the top at rest. One big thing about rolling things is that it must say it rolls without slipping. If it says it's slipping, then you can't solve for it, because if it's slipping, then there's a disproportionate amount of K that's not being used, or K rotational that's not being used. Because if you have a ball that's slipping along, like imagine like a ball that slips along ice. Sure, it'll roll, but it won't roll as much as it would on asphalt because it's allowed to slip. But if there's enough friction to keep it rolling, then, and it'll only roll if there is friction, then it will tell you rolls without slipping. Although, of course, we could also solve this problem where we say this entire thing is frictionless, and then we just have a cylinder with mass 100 kilograms that doesn't matter about the moment of inertia, because if it rolls with no friction, then it's going to roll only with slipping and without rotating, since we need the friction for it to rotate. Then we just have a normal problem, and it's as if this were a box. We just have a normal problem with only kinetic energy, but we don't. So we have K-rotational because there's friction, but you'll see the friction, the fact that there is friction won't matter, except for the fact that we know that there's K-rotational. So let's go ahead and solve for it. We have this whole thing up here. E naught plus work is equal to E final. Okay, well, first of all, I would like to just clarify something. Just because there's friction doesn't mean that there's going to be work done that removes energy from the system. When we have something that is able to rotate, the point at which it contacts the ground stays constant the entire time. I'm going to try to find something circular while explaining this concept. The point at which it makes contact with the ground stays constant the whole time as it rolls, assuming without friction. So I'm going to use this Aquaphor bottle here to model this, and I'm going to draw a line straight down the bottle, and hopefully, if I do this right, hopefully it will, when I roll this, it will leave a mark that is equal in size to the mark that I laid it at, which is exactly what we saw happening. That tiny mark there, you can barely see it, is the same width as what came off of it there. So, and that is proof that that little line I drew on this, I just erased it, but that line I drew on this, it only contacts it on that line when it's rolling over that. So friction will only allow it to roll. It won't take away energy from the system because you need a distance for it to travel, for it to do work, because work is equal to force times distance. Well, if that point stays constant the whole time, there's no distance that it travels, and therefore this is infinitely close to zero, work infinitely close to zero. So we know that our starting energy is the height of this thing. We have 5 meters. It's not the length, it's just the height. So we have UG is equal to, at the very bottom, we're going to have a K rotational, and then also just a normal kinetic translational energy, because this thing will be moving downwards here as well as spinning. So therefore, we're going to have both K rotational and that. So now let us solve for everything. We have mgh is equal to K rotational, so 1/2 I w squared plus K final 1/2 mv squared. Now let's really quickly take all of this stuff and get it down to only the terms we need or want. I'm going to go v is equal to question mark. Because right now we have this moments of inertia and angular momentum that really look ugly when we're looking for velocity. So we're going to say mgh is equal to 1/2 mr squared times angular velocity squared, which would be angular velocity is velocity divided by the radius squared, plus 1/2 mv squared. You'll notice that this squared means that we're having radius squared divided by radius squared, so they will both cancel out. mgh is equal to 1/4, not half, because 1/2 times 1/2, m, the two r squareds cancel out, mv squared plus 1/2 mv squared. Oh, perfect. mgh is equal to 3/4 mv squared plus 1/2. Oh, no, not plus 1/2 mv squared. Just 3/4 mv squared. Because 1/4 plus 1/2 is 3/4. So now that we have this equation here, we can use that to solve for final velocity. So really quickly, I would also like to point out that this here, if we didn't have a rotational, would just be our K. But because it's also rotating, it is that. And also, one more thing I would like to do is that I would like to have you notice that it ended out when we simplified this down to that, it looked the same exact thing as our kinetic energy, but multiplied by the constant in front of the I. And that's exactly what I want you to notice, and that will actually allow you to take shortcuts. You can just say is equal to, you can say K rotational is equal to the constant attached to the I times K, which would mean that if that constant was 2/5, it would be 2/5 times 1/2 mr squared, or 2/5 times 1/2 mv squared, not mr squared. So then it would be 2/10, so 1/5 mv squared. So now that we have this here, we can solve for our total velocity at the end. So mgh is equal to 3/4 mv squared. mgh 3/4 mv squared. So we would have 100 times 10 times 5 is equal to 3/4, 100, and then velocity squared. So we can take out 2 100s from there. I forgot to just negate the masses here. So 50 times 4 divided by 3. 50 times 4 divided by 3, all under a radical, is 8.2. Velocity equal to 8.2 meters per second once it reaches the bottom. There we go. And that would be our solution, how fast it's going, and our use of Kᵒₒₜ. And that there, finally, is all of energy.